Hi, good morning to everybody. Today we are at SFF Samsung Forum, and I'm going to give you a presentation regarding full solution for AI application challenges and opportunities. So during the lecture, we will touch the main design consideration for AI application, including a RISC-V platform implementation in our experience of leveraging Samsung 40nm FinFET technology for artificial intelligence. Okay, a few words about Avnet ASIC. Avnet ASIC is design solution partner of Samsung. Together, we provide comprehensive ASIC design services and supply chain management with Samsung Foundry. We have a proven design record and expertise of Samsung Foundry processes offering. And together with Samsung Foundry, we have collaboration which provides easy access, fast business proposal, experienced design services, and Foundry OSAT operation. Okay, so regarding artificial intelligence market, you probably all aware AI is surrounding us everywhere. AI market is valued at 40 billion in 2019, and it expected to grow by 40% from 2020 to 2027. There is continuous R&D development by the tech giants, which drive in adoption of advanced AI technologies in different industries like automotive, healthcare, retail, finance, and manufacturing. AI is proven to be the significant revolutionary element of the upcoming digital era. The AI hardware market is dominated by GPUs and CPUs, and this is because of high computing capabilities which are required by AI applications. So a few examples of the areas where the GPU can be implemented for the AI is edge server, where you need high performance and also low power consumption and scalable solutions for different video applications. It's autopilot, where for the autonomous car, you need high reliability and high performance autopilot chips inside the vehicles. Acceleration cards, which provide high parallel computing performance for internet, cloud, military, scientific research, enterprises, medical devices with a dedicated acceleration card server. And there are a lot of AI models inside the industrial applications, which both require low power consumptions and high performance models for industry application and agriculture. A few words about the typical synergy that we have with the AI customers. Usually the customers that develop AI applications are the startups that would like to focus on the main AI engine and know-how that they bring to the market. So that's why they develop their own AI models, and they required software and hardware infrastructure for that. We, on the contrary, together with the Samsung, will provide to them the solution, so everything around it. So either IP or interface integration, if it's multi-core or multi-CPU SoC solutions based on the RISC-V platform or any other CPUs, backend layout implementations from RTL to GDS, the package development, the board development, the production testing, and eventually the mass production management. So the idea is that the customer will come to us with his own IP, and we will help to develop him the chip and eventually bring it to the mass production and manufacturing by utilizing the Samsung facilities. Samsung will provide the whole ecosystem around it, the access to the most advanced nodes, the silicon manufacturing, the access to the foundry IPs like PLL, PVT, OTP, and all the technical support and know-how which is required to manufacture and to reach a good yield at a quite advanced nodes. A few words regarding the Azure Engine and Avnet partnership. Azure Engine has chosen to partner with Avnet to bring their proprietary parallel processor AI architecture to market. Azure Engine first is leveraging the 30+ years of ASIC design experience that Avnet teams has inside and to develop and manufacture their solutions in quick time to market. In addition, Azure Engine will be added to Avnet Inc. ecosystem to enable new artificial intelligence, machine learning, and crypto mining application with Avnet global customer base. So by leverage the Avnet distribution channels, Azure Engine will be able to sell their product globally. Avnet will help launch both the custom ASIC device and also system-level accelerator cards with the goal to distribute the Azure Engine's products over the world. The RPP core overview. RPP is basically the know-how, the AI IP engine that developed by the Azure Engine. This is a reconfigurable parallel processor that brings the AI architecture to the next level. I'm personally not an expert in that area, so I will share the information that I got from the Azure Engine, which is really specified and the creative know-how in that area. So they have a unified architecture for parallel processing algorithms. They have a full scalability without any change to the software. They quite low power and a high area efficiency. So here you can see the whole ecosystem around the RPP. It starts from the known TensorFlow by using neural network libraries, the graph compiler, the NVIDIA CUDA compiler, ISA simulator, which connect together software and hardware. The hardware processor architecture, there is a data flow architecture that controlled by instruction dispatched from the sequencer, as you can see on the right side. It propagates to the processing elements. There is up to 32 processing elements that execute SMIT instructions. Not everybody familiar. There is SMID and SMIT. SMID is single instruction, multiple data, and SMIT is single instruction, multiple thread. So it allows in the single time to distribute and to all the processing elements the instruction and execute a lot of data in parallel. Each process element has 32 ALU elements as a vector, and there is a circular data that with arbitrary program lengths that can be configured. It also supports the CUDA language. With CUDA language, connect actually between the RPP hardware architecture to the SMIT programming style. Massive parallelism, so support by single core. As I mentioned, there is 32 process element. Each element has 32 ALUs, so together it brings to 1024 ALUs per core. There is max 16 instructions that allows to perform 16 max extraction per cycle, and it enables efficient matrix multiplication, convolution, and other operations. So it also supports the floating point, the brain floating point, and the integer instruction. Here you can see the compare of the Azure Engine solutions via existing the solutions on the market. It can be better and smaller, which is quite unique. So you can see the benchmark for the ResNet 15 algorithm, which is a lot of time used for the compare between the different AI, and you can see that it's quite efficient compared to the other solutions. It also has a smaller area and the smaller power consumptions, which eventually brings to the better QR. So as I mentioned, the R8 single core, the performance, it has 2024 ALUs, and it can reach up to 16 teraflops and 32 teraops. There is full HD 32 channel, 30 frame per second video capabilities, and the access to the external world provided through the PCI Gen 3 with 4 lanes. The DRAM capacity can be up to 8 GB with LPDDR4 and 4X, and the bandwidth is up to 50 GB per second. There is an option to increase the capabilities and to use not only 1 core, but to use 4 cores, where you will have 4 times 4096 ALUs, 64 teraflops, 128 teraops, and etc. So basically everything is increased by 4, multiplied by 4. Okay. So for the implementation of the AI engine, we have chosen together with Samsung 14 LPP FinFET process, and there are several reasons when we evaluated it, and by several technology parameters. The first one, the metal stack. We will touch it later, but we were required to use a higher metal stack in order to create a solid power mesh, which is required for AI, and the fast clock tree structure. For the standard cells, we have used the 9-track high-performance library from the ARM for the Samsung 14 nanometers. We have compared it with 10.5 track, and we have found that by using high-performance cells at the 9-track, we were more efficient both for the area and timing, and for the congestion. So that's why we decided to use for this standard cells library. For the memories, for the Samsung 14 nanometers, we have used the ARM memory compiler, and due to the nature of the design, almost all memories were used built-in pipe out. Also, by leveraging the Samsung Foundry IP team, we have used Samsung IPs as different types of PLL, process voltage temperature sensors, OTP, and fuses. All the IPs that you see here, they both support 0.8 volt and 0.9 volt. This allows us to have power efficiency and performance mode without do any changes to the design. Overall, these parameters drive us to choose 14 LPP technology as a good sweet spot for cost versus performance for the AI chip. Okay, so now we can discuss RPP, so-called reconfigurable parallel processor. As you can see, it's quite a big design, which have more than 50 million instances. It has 200 megabit memory. The operation frequency is between 800 megahertz and 1 giga. Fully synchronous design. There is a special architecture for the memory share that all 200 megabits of memory can be shared between the different process elements and leverage the memory capacity. So when we started implementation, so basically we had first for the block partition we have 16 process double engines. Each hard macro has 2 engines, which bring us to 32 process elements. They were all connected by abutment and located in the center. Memory units were placed above and below, and that's allowed to share the data between all the computing units and to have the data flow that memory can be shared between all the processing elements. We didn't use any known interface. It was used by the unique Azure Engine dedicated interface, which allows to have a low latency and to access each process engine. All engines and memories, as I mentioned, were fully synchronous and run at 1 gigahertz. On the right side, you can see the interface unit, which were interfacing the external world. I mean the rest of the chip. And this was the only interface how you can access the RPP module. It also was running at the same frequency, but asynchronous to the RPP itself, which allows to easily to separate the RPP from the rest of the chip. Okay, so when we started the backend implementation, one of the biggest challenges that we had for the AI model is how to synchronize all the memory units and all the computing units, processing units between them, because it's running at quite a high frequency. And on one side, on other, we didn't want to use any asynchronous interfaces inside, because it will reduce the predictability of the data flow. And also, we didn't want to add a lot of pipes in order to not to reduce the performance of the AI engine. One of the biggest challenges for the implementing the synchronous design over the big chip area is the clock tree. There are many conservative approach like clock tree mesh or H tree, which are used by the big companies in order to synchronize the whole design, but the penalty for that is the power consumption. After several evaluations, in order to both to implement it fast and to have fast turnaround flow, we decided to use a regular Synopsys ICC automatic tool for the clock tree building without any special features as H tree or clock tree mesh. We did develop a special clock tree buffers, and together with routing the clock tree over the higher metals like G and K metals, which have a very low resistance on one side, and on the other side do provide the flexibility to have still a big amount of routings of that layers. We succeeded to reduce the clock tree latency and to balance the different process units between themselves and also the memory unit. So overall, we have a latency around 2 nanoseconds, quite so not a big latency for the big area at something 14 nanometers. And we have only the small channels between the memory units on the upper side and on the lower side. We didn't have any feed through the blocks, and the block itself was implemented in the regular CTS automatic flow. That allows us to have a fast turnaround and not each time to reduce the partitioning, to change the blocks, and only to deal by the bottom-up approach when you first finish the implementation of the block, and then you do the implementation at the next upper level. We did have a high global skew between the different units, and where it was necessary, we have solved it by adding the pipes in the required places. Another challenge that we have is the power consumptions and power activity profile. For one of the unique challenges that exist at AI design is power activity. AI engines, due to their nature of parallelism and to execute as much many instructions per cycle in order to improve the performance, they have a quite high power activity, up to 25%, what we say, which is much bigger than other usual designs like a CPU or communication modem. They also have very short and fast power peaks. The power consumption can be changed during several hundreds of picoseconds for one process unit, and actually it happens to all of them together because it's a synchronous design and all the design toggle together. So the solution that we have suggested and implemented, it was to have more dense and massive power grid. Again, it was possible due to the fact that we selected a higher metal stack. We have used both decoupling on die and inside the package and on the board in order to reduce dynamic airdrop peaks. We have created an artificial clock skew between different processing units in order that not all the units will toggle together at the same picosecond, because if you balance the clock tree too good, actually you will have you can have a bigger airdrop issue. So that's why we actually deskew a little bit the blocks between themselves. And also, together with the help of the customers, we used a vectorless approach and VCD-based patterns already on RTL in order to find the problematic spot and improve it, and still to save time and not to have a long turnaround cycle between the RTL implementation and the backend implementation. Okay, so once we have finished with the implementation of the RPP and we started to discuss the full chip, we also saw several challenges there. So the RPP itself is quite a big block, and it's implemented in the middle of the chip, and around it you will see 4 LPDDR4 interfaces with 32 bits with each of them, several video engines, PCI Gen 3 4 lanes for the communication, and RISC-V multi-CPU platform for the data flow control and for the different other tasks. Also, you have general blocks like PLLs, PVT, OTP, and etc. As I mentioned, both on the chip level, all IPs support 0.8 and 0.9 level core supply that allows to have two different performance and low power modes. Okay, so 4 LPDDR4 interfaces were used for the external memory access, and when you access the LPDDR4, you already have a latency. So each LPDDR4 controller has multiple number of XI ports, and each XI port and XI channel was independent in terms of frequency and asynchronous to other channels. Each XI channel was sampled and piped according to the physical distance from the source, and it depends on the running frequency. The main challenge, one of the challenges, was to find the balance between the DDR latency to the DDR, the number of samples, and the overall performance. So the challenges, as I mentioned, were the following. Since we had RPP in the middle, we have long passes due to the physical distances. We need to go around the RPP to each of the IPs of the LPDDR. As I mentioned, the output of the reconfigurable power processor was on the right, where was located interface unit, and then you needed to go around the model to reach each of the LPDDR4s. And basically, wide DDR interfaces, they define location both in the package and inside the die, and they define the floor plan of the full chip. And the short in the width and long channels, they created potential issue for the routing and the congestion. So the solution that we used in the full chip was the opposite for the solution that was implemented inside the RPP. If the RPP itself as AI was fully synchronous in order to maximize its performance, for the reaching the video engines, LPDDR4 and etc., we use the asynchronous approach. We have multiple PLL structures that allows independent frequency control per each independent XI channel over each of the IPs. And each hard macro on the full chip has an asynchronous interface. So for example, the RPP itself, as we mentioned, had a 2 nanosecond clock latency inside, but towards the full chip, we had the asynchronous bridge inside, so the latency was invisible for the full chip. And all hard macros were connected with point-to-point asynchronous protocol. And we tried to have small number of XI router blocks in the full chip level. For the full chip, due to the nature of it, that we had many of the long channels, we try to keep only point-to-point connectivity between the different macros like video engine, LPDDR, and RPP, and each of them have several EXI ports, and they were connected point-to-point, and all the routing network and the routers were hidden inside the block, so it allows to connect and use much smaller number of routing resources in the top, and eventually to implement, to successfully implement the full chip timing and routing at that level. A few words regarding the multi-CPU platform. For the multi-CPU platform, we used our RISC-V that we developed on the RISC-V architecture. Instead of putting big and strong CPUs, we put small RISC-V CPUs with very small 2-pipe core architecture running at 500 MHz. They allow to have high code density, to run the simple RTOS or even a bare metal drivers on them. And they were responsible for the boot sequence, for the initial configuration of different IPs, and also for the video DDR reconfiguration. And for the inter-CPU communication, we used a known approach like mailbox and semaphores, and that allows to have a good and flexible data control over the whole chip. So for the summary, AI chip present quite unique combination of backend implementation challenges. You need to balance between size, power consumption, power activity, synchronous and asynchronous architecture. You need to perform correct design partitioning for the synchronous and asynchronous parts. We as Avnet ASIC offers complete set of customized developed services that enables AI customers to keep focus on their core business in algorithm and applications, to put the focus on develop the IP itself, and we will have them to create all the ecosystem around it. Samsung Foundry offers 14 LPP FinFET as a sweet spot for cost versus performance for AI chips. It's possible to reach quite a good performance without going to more advanced nodes. And we are confident that Samsung Foundry, together with Avnet ASIC as design solution partner, will bring your project, AI or any other application in fast time to market, with optimizing cost and maximizing your technical performance, and eventually help you to reach the mass production. Thank you very much. It was a pleasure to present it, even in such Corona days. Thank you.